Okay, so let's start. It's a great pleasure for me to introduce to you Professor Piotr Sulkowski from the University of Warsaw in Poland. And he's going to talk to us about Calabi-Yau Lattice paths and BPS counting. Please go ahead, Piotr.
Thank you very much for a chance to speak here. So that's indeed the title of my talk. It might be a bit misleading, but I wanted to make it very close to the title of the conference. So as you see, I just replaced Calabi-Yau crystal by lattice paths. And well, this is so because, as you all know, Calabi-Yau crystals in very nice and cute way encode some complicated structure of BPS counting. So it turns out it happens similarly in related setups where lattice paths arise. And you might think of lattice paths also as kind of crystals, or maybe you would be able to relate the paths I will show you in a few moments to some also 3D crystals, as we have seen in some other slides and presentations earlier. So, well, I say that it may be a bit misleading because maybe I should have added the word open somewhere here. So in fact, what I will be mostly interested in will be open BPS states related to some branes and a class of BPS states which arise in that context. So let me first show the scheme of kind of a talk or table of contents. So the lattice paths I will consider more precisely are, or we refer to as generalized Schroeder lattice paths. And these are the paths that we consider mostly in the second paper I listed here with Marko Stosic. However, we also had some hints that they play a role in this first paper also with Marko Stosic and Miłosz Panfil. So these are basic two papers I will refer to in this talk, but in fact also to many others which I don't list here. But anyway, I will tell you in a few moments what are these Schroeder lattice paths. But let me stress that they are encoding some information about, well, in string theory interpretation about BPS states related to branes in a bit more general toric Calabi-Yaus, but in fact, yeah, I will focus in this talk on the system where we have some branes which engineer torus nodes. So this is the same class of nodes which appeared, I think, in the first talk in the conference. So this is what I mean. It's misleading. It's not very fancy system. These are, you might say, just torus nodes, but there is a way to engineer them in string theory, of course. And well, you know there is relation between this system and this system, which goes through Chern-Simons theory. But what is also interesting that this information can be also captured in terms of symmetric quivers. So this is a class of quivers which plays similar role to BPS quivers in for the equal to theories, but they arise in the interpretation of 3D and equal to theories, which provide like effective description of those systems. So this relation is, I guess, very well known, starting from Witten in '93, and then papers like Oguri-Ewafa around 2000 and many others that followed. So there is a way to engineer torus nodes by some branes intersecting S3 in deformed conifold, and then by geometric transition you get a resolved conifold. And then you can consider BPS states, open BPS states in that system. You can check their integrality. What is quite nice that you have a lot of testing well, data for testing various conjectures, because for torus nodes, essentially the amplitudes in these geometries are expressed by some knot invariants, such as colored polynomials. So there are many of these colored polynomials, so they can be used for various tests, and you can indeed determine that various integral BPS invariants arise from this this set of colored polynomials, but until recently it was not quite clear if there is some order or whether one could understand that data in some simpler way. And then it turns out that it can be done in terms of the symmetric quivers, which in a very concise way capture the information about all these invariants. So this is what we now refer to as knots quivers correspondence. And this is also what I've been working on for last few years with some of my collaborators. We wrote a paper with that title with Piotr Kucharski, Marko Rajnek, also Marko Stosic a few years ago. And since then, I've been working on that. So now the aim of my talk is now find relations of this system to some specific class of lattice paths, well, and also explain these different interrelations. So I will start telling you what are these lattice paths, and then I hope to explain how they relate to these other corners of that picture. So yeah, let me start here. So by lattice paths, I mean paths which can be drawn on a square lattice. And first of all, let me think for a moment what kind of information I'd like to encode. So I was not maybe very precise, but main objects which appear in this context are colored Complete polynomials. I will denote it by P with index R, where R denotes the color, and the color is, in general, it may be any Young diagram, but I will consider Young diagrams consisting just of one row, and then they depend on two parameters A and Q. You must be well aware that in Chern-Simons interpretation, Q captures the level, and A is Q to power n if we have a SUN gauge group for Chern-Simons theory. So to represent this information for torus knots, I'd like to encode information about this Q, about parameter A, and also about the type of torus knot I am considering. So it works as follows. First of all, to encode the type of a knot, I consider a line which has some rational slope. Let's say I'd like to draw a slope 2/3. And this is some fixed line which I have in this system. So when I say torus knots, let me add also in the bracket of type M, comma, N. And then the paths I'm going to consider consist of 3 steps. It can be a step to the right, it can be step up, and it can be a diagonal step. So some example looks like follows. Okay, and then the information about the parameter A is encoded in the number of diagonal steps. And the information about parameter Q is encoded in the area between this fixed line and a given path that I am considering. So again, I am fixing this blue line and then consider all possible paths made of these 3 steps, and these paths have to end in rational points. So if I have some integer slope, they have to end here, and the number of that point corresponds to a specific R which I have here. So now what I introduce is the following generating series of those paths. So I introduce extra generating parameter X. And well, this is just the notation. So the coefficients here, I call them n with indices IJL. And then this Nijl is equal to the number of those paths made of these steps from the origin to the point NL, ML. So N and M is fixed and gives the type of a torus knot, and let me call this L equal 1, L equal 2, and so on. With I have diagonal steps. This one half is just for a convention, and to agree with some notation I will introduce later. And area, I don't want to write too many words here. By the area, again, I mean this area between violet path and blue path. This area being J half. So this is supposed to be some quantum object. We will see why. So let me just mention a few special cases. If I fix Q to be 1, then I will refer to this as classical case or classical paths. By the way, if I choose M and N equal 1, so I have just diagonal blue line, then I get something which is called original Schroeder paths. And also, in fact, Q equal 1. So these are paths that Schroeder considered originally. So by this word generalized, I mean introducing other slopes and also this Q deformation. If I fix N over N to be 2/3, so in fact, this is the example just in this picture, and then also Q equal 1, then I have some class of paths you might have heard of, which are called Duchamp paths. So these are some classical paths in combinatorics. So in that case, their generating series is given like starts as follows, in case you have seen that somewhere. And finally, if I just have M over N equal to 1 and Q equal 1, and if I forget about, I can also forget about diagonal steps, so put A equal to 0, and then I have Catalan numbers. And well, slightly more general case, if I have the following slope 1 over F, but also Q equal 1 and A equal to 0, then I have some class which are called fuzz Catalan numbers. So the Schroeder paths or generalized Schroeder paths capture various kind of standard objects in so-called analytic combinatorics. So in the rest of the talk, I'll be interested in this generating series because it turns out it reproduces various objects which we are interested from these other viewpoints here. So let me now write a proposition. And well, maybe I can erase these examples if you have already taken note of those. These are just some simple special cases. And I will also erase this. So now the proposition is, or however you want to call it, claim, or theorem, or maybe more properly conjectured. So the statement is that this is equal the ratio of the following of certain generating series associated to quivers. And the quivers that appear here are quivers that arise in this knots correspondence, and these are quivers associated to torus knots. I will still say in a few moments what how this works, but let me just explain what I mean by this different symbols here. So see with this bar here, this is quiver or matrix encoding a quiver. And I put this bar because I mean here this is quiver which encodes so-called unreduced colored conflict polynomial. So these are unreduced means that this is some specific normalization of colored conflict polynomials. For the moment, I will not introduce that, but let me say that there are different normalizations. So the one for which the unknot conflict polynomial is equal just to 1 is called reduced normalization, and this unreduced one is such that for the unknot we have Q number as the value of conflict polynomial. So unreduced quiver matrix for unreduced colored conflict polynomials for Mn torus knot. So this is how information about a knot is encoded here. And in addition, it has to be taken in specific framing. So framing is some integer parameter which you have to specify when you compute various knot invariants. And in this case, this framing has to be equal to m times n to see this nice pictures.
So there's a vector level for color. I mean, it's a color conflict. So each color.
Yeah.
So
Maybe I should write R.
so L is the color. Oh.
Yeah. The point which I am here, this gives me.
Oh, it's
So now, what is E bar C? It depends on a single parameter x, but in fact, this is a specialization of some generating series associated to a quiver. I will write in a moment how this generating series looks like, but for a moment, let me just say that the idea of this knot quivers correspondence is that to a given knot, you associate some quiver, and in case of this unreduced invariance, this quiver has even number of nodes, and to each node, we have associated one generating parameter. So I don't know this generating parameters x1 up to x to k, and then I have to specialize them in some way, which is as follows. There is some sign. There is a power of a, which I will not give you in detail now. It's some technical remark. And then there is x in power 1. So this is how this dependence of x appear. And finally, this P. Now, in general, if I have some symmetric quiver, so if I have a quiver matrix C, then generating series for that quiver takes the following form. So there is Q to quadratic power in this label is d1 to dm. They are also called as a dimension vector. And then in the denominator, I have Q-Poch hammers. For each of those Ds, I have one Q-Poch hammer. And then Xi's just in linear powers. And well, this is some generating series which you associate to, again, to a symmetric quiver. Let me draw just one example. By symmetric quiver, I mean a quiver which has arrows which arise in pairs. So for an arrow in one direction, I have also necessarily the arrow in the opposite direction. And well,
That's because you want to have the C matrix to have a special or can I not use a generic quiver?
you could, but then there is some theorem which I'm going to write now, and it works for symmetric quivers. That's one reason. But the more important reason for us is that precisely such symmetric quivers arise in these problems that we consider. So these quivers which are associated to nodes and which capture this BPS invariance associated to nodes happen to be symmetric. And in fact, this is more general than nodes. You can also generalize this system to other toric freefolds with other types of branes. For example, you may take Agana-H-Wafa brane for more general geometries than just the conifold, and the open BPS states in that system can also be encoded in some symmetric quiver.
So this is a some type of expression which appears first in the domain stock, and then I guess your quivers are different. Is it true that the quiver you have and the quiver he has are different, or like
So let me just say that Cij, still discussing this expression, Cij is the number of arrows between vertex I and vertex j. So this is adjacent matrix. So the symmetric condition means that, well, this matrix has to be symmetric. So there's some important difference when people tell word num-sum, typically they mean Q series, so that there is no generating parameter, it just depends on Q. But this factor is similar, and that can be also Q in linear powers. So you may get some num-sum, but specializing those Qs to some specific values. But for us, what is important is that we have these generation parameters. But aside that, indeed, the num-sums that were in the previous talk are of similar form. I mean, you can interpret this quadratic factor here as encoding coefficient of some figure as well. Even though when Lam was writing his paper, and in that context, typically you think of quivers. So what is the reason quiver appears? Because of what I'm going to say now, because of this equality. Because when people in representation theory consider quivers, they want to understand properties of, for example, their moduli spaces. And this moduli spaces, some topological characteristics like some kind of Betti numbers and so on, are encoded in so-called DT invariants for quivers. And these DT invariants can be obtained by factorization of this formula. So this is the place where indeed the relation to quivers arises. So now there is a statement. It was conjectured first by Kontsevich-Fabelman and proven by Efimov, and I think there are also other proofs. So the statement is that you can write it in factorized form. And let me stress that I'm still now discussing general quiver, not necessarily related to nodes or lattice paths. And so we have factors which look like Q Poch-Hammers if you fix D, and if you fix J, then this factor would look like Q Poch-Hammer. But here we have extra exponents which are called DT invariants for quivers. And as I said, they encode properties of moduli spaces of the quivers. So what is also quite important is, and this is what was proven by Efimov, is that these gadgets are integers, non-negative integers. So maybe I will not write more symbols, but let me just say in words that similar factorization happens in the Oguri-Wafa conjecture, and there are BPS invariants associated to nodes which arise from similar factorization of topological string amplitudes. So one of the advantages of this node-quivers correspondence is that we can relate that invariant to these omegas, and essentially we can express them as some combination of these omegas with integer coefficients. So this is what explains integrality of the Oguri-Wafa invariants, all LMOV invariants. So, okay. again, this is the statement for quivers, but the line above is the statement that this generating function of lattice paths can be expressed through this generating series of some specific quiver which is associated to a torus node. So in other words, these torus paths encode in some smart way all these colored invariants, and they are captured just by this quiver I have to use, and well, a few other numbers which are here in the exponents, but this is finite amount of data, which gives me the whole infinite series of not polynomials on one hand, and then those lattice paths. Okay, so one statement I wanted to make is this one. And let me also rewrite it in some other way, which makes yet more explicit relation to some knot invariants. Okay, so that dot means this also equal to the following expression. I hope I will fit in this line. So this is the expression which, well, here is some prefactor which can be interpreted as assigned to the unknot in general. There is A in some specific power and Q in some specific power, and also X just in power R, so this is generating series in X. And then there is a factor which is different for various knots, and this is a specialization of so-called superpolynomial, also for Mn torus knot. So that's a bit tricky, because so superpolynomial is some generalization of Humphrey polynomial, and you can think of it in the spirit of categorification. So in general, such an expression arises, or in some cases is believed to arise from considering homological knot invariants encoded in these homological spaces. And then if we specialize T to be equal to -1, then we get Humphrey polynomials, colored Humphrey polynomials. But what I do here is in fact another specialization. So I forget about dependence on Q, which appears in Humphrey polynomial, but this Q, which on the other hand appears in this path counting, I relate just to that parameter T. So again, there is direct relation between not this invariance of torus knots to these paths, but the subtlety with the relation to quivers is that this identification of parameters is different than in the knot quivers correspondence. And this is also the reason why a quiver which encodes lattice paths is a bit different than in the knot quivers correspondence, because I have here also to consider quivers for those unreduced paths which are twice larger. So if this is quiver for trefoil knot, then the quiver which encodes paths in the system is twice larger, and we have a prescription how also how to find it.
For torus knot, is your Cij matrix positive definite? It's positive definite. Is it positive definite?
You mean whether it has positive?
Yeah, whether C is positive definite for torus knot cases.
By positive definiteness, you mean whether it has integer entries?
Yeah. No. The eigenvalues, all the eigenvalues are positive. Some positive.
I'm not sure. I must say. I got
Because of
to
that.
think a bit. But yeah, I'm hesitating because in fact we have some freedom here. So as I said, in the context of paths, we have to fix this framing to specific values. But in general, you may consider different framings. And a change of framing alters not invariance a bit, but it's not a big difference. And a change of framing of a node corresponds to changing entries of a quiver matrix by one, all the entries by one. So we can also change all entries by any, in a sense, the same integer you want, and you still characterize the same node. And in this process, the eigenvalues might change. So even if for some specific framings they are not all positive, then you may, in particular, you can always change this matrix to have all positive entries. Because in some framings, if you consider it, might turn out that some of the entries are negative, so maybe it doesn't have immediate quiver interpretation, even though the statements did.
Another question. I'm a little bit confused that A is some number, right? They're A, that's diagonal.
Well, it's like a generating also some parameter which we have arbitrarily. We don't fix it to specific value.
I see.
So in string theory, it corresponds to this modulus of P1 in resolved conifolds.
I see.
Or A is equal for complete polynomials as Q to power n, like in John-Simon's theory. But we keep it generic.
Matrix is also definite defined only if there's no arrows between any pair of distinct nodes, and for each node there exists at least one dimension. Doesn't linear that.
Okay, it could be so. I didn't think that much of that. Okay, so what would I like now to? To add, maybe let me. Let me just add one more clarifying statement about this not quiver correspondence. Okay, I will erase this picture. So in that context, one associate to a node or to some brain system some partition function or generating a series which looks as follows. One considers colored polynomials again in some specialization. And then, as I said, they can be expressed as generating series, but with other specialization of those x's. So there is some sign, there is some power of A, also some power of Q and X. And then the C, which arises in this ordinary Gauss-Quiver's correspondence, is a quiver which is like in this picture. And now I consider this quiver which is twice larger. This is what I said already. And this is also a difference between this generating function for paths and generating functions for ordinary invariants. So maybe let me give some simple examples. So if I have the situation with a slope being just 1 over f, so this line is something like this, then the quiver I have to consider, or which arises, which encodes lattice paths under this slope, is has the following form. And in this case, this generating series. Well, it has just this form. And in this case, we get Catalan numbers. If I have trefoil, not then the quiver which we have to use is related to this one. So it is certain the doubling of that quiver. So if this quiver has size 3, then I have quiver which is of size 6. Maybe I will not write the whole one, but there is some explicit data for that. And let me also mention that we have some explicit formulas for these BPS numbers that appear in this exponent. So in this context of not here, they are referred to as LMOV invariants, which can be also related in some way to those coefficients, Nij. I mean, we have explicit formulas in the classical limit, but closed formulas for both those coefficients Nij and those dt invariants which appear in that context. For so let me be slightly more general again. Now what I would like to consider is a generating function which appears on several generating parameters. So this formula can be obtained as a specialization of such an expression, which is the limit when q goes to 1 of the analogous ratio of those quiver series. Now, for a moment, let me again consider generic quiver. And when I take this ratio and limit q to 1, let me denote the coefficients that arise by b with indices L1 to Ln. And they also, this expression can also be factorized. And in fact, this is the relevant expression for which it makes sense to consider classical limit. So it quite does not make sense to consider classical limit just for such a P, because such a quiver generating series, it is related to topological string amplitudes, and it behaves like 1 over h bar and 0 and so on, where q is exponent of h bar. So when I take q to 1, which is like h bar going to 0, then I have just some singularity. But if I have the ratio of such two expressions, I can in fact factorize both of them in the spirit of this factorization into quantum logarithms, and then the terms which produce that singularity cancel, and then I am left with an expression which is well defined. So these omegas which appear here are simply the resummation with the omegas, with those omegas with extra label, which I had found from factorization of this expression. So these omegas with this extra label J are referred to as motivic dt invariants, and These are often called classical DT invariants. And again, what I'd like to stress is that we can find explicit formulas for both these omegas and also those coefficients B. And there is, well, they are given by some closed formula, but this is combinatorially quite non-trivial. So let me just give the simplest example. If C is given, if C is just 1-by-1 matrix, so again, let me erase those. So if this is 1-by-1 matrix with entry F, then I have just a single coefficient Bi. And what is quite non-trivial is that this is integer. Even in this simple case, this is quite non-trivial. If I wouldn't have this 1 here, then that immediately you would see that this is not integer. If you take f and I equal to 2, and if you wouldn't have this 1, then something like this, that would be 4/2, which is 6 divided by 4 would be 3/2. And here we have the statement that all these b's must be integer, which is a consequence of this decomposition and this proof of integrality of DT invariants. And so also just these statements give us some non-trivial predictions related to number theory. And well, the expression we get are similar. So there is some sign and there are some denominators and some binomials. So even from these two examples, you may kind of try to guess what would be general pattern, but combinatorially it's quite difficult. So I'm afraid I wouldn't have time to explain all details. But just by saying that, I want to stress that we also have explicit and closed formulas for these numbers of different paths and also corresponding invariants associated to knots.
So you have a remarkable combinatorial identity already in the simple examples.
Yes.
I wonder how you managed to find it.
Well, by some trial and error and
Trial and error.
So for example, let me stress, if you take m over n, yeah, another example. I will not write the detail, but this case, so like the next simplest after Duchamp paths, it was a big puzzle in this community of combinatorics. People were wondering how to write generating function of those paths like in some concise way. And we do that easily. We just take quiver corresponding to free gamma portal plot, and we just have this quiver generating theory, which gives the answer. So
Oh, I see. So actually, I see. So what it means that even for people interested in the path only, not the quiver, and
yeah,
it actually generates a new result.
Yes, so that's quite interesting. Again, so we can hopefully also make some contact with that community. So yeah, again, these paths are, maybe let me summarize, I have last few minutes. I hope that these paths give some new playground for testing various ideas related to BPS states, and as we see, they are related to knot theory and quiver representation theory, and all these systems in string theory related to that. So, well, just to summarize, a few remarks. Maybe I said some of them in words, but let me write them quickly. When we want to count these paths, they are captured by finite data, namely the form of a quiver, and I have those powers of A, but these were just some finite set of numbers, and it gives me generating the numbers of this paths for all the points on this diagonal line. I should also stress, yeah, I didn't write that in detail, but in fact there is something that we call elementary paths. So these are paths which, in that picture I had, start from the origin and end on this first integer point on diagonal. So there is just a finite number of these paths, for example, this one, and it turns out that they are in one-to-one correspondence with nodes of the corresponding quiver. And on the other hand, we know that the nodes of that quiver are in one-to-one correspondence with generators of Humphrey homology. So in fact, well, we don't understand all details yet, but we very much believe that some structure of these paths can shed light on knot homologies. And in particular, one might also wonder if there is some kind of categorification of this picture and whether such a categorification could be related to those knot homologies more systematically. And another remark is that this generating function of paths, similarly like analogous objects for knots, satisfy some algebraic equations which are referred to as A polynomials in knot theory. So essentially there is some polynomial in two variables x and y such that the following equation holds for polynomial A. And also there is corresponding quantum A polynomial. So one can think of quantization of this A and then A hat with some operator arguments annihilates that P C now with all dependence on all parameters, including Q. So, well, maybe let me end just with obvious question. What about other framings? This is a mild, maybe, modification. And we see experimentally that if we change framing, we still get some generating series which have some combinatorial interpretation, but we don't see that systematically. But apart from other framings, one might consider other knots, not just torus knots. And in fact, if one considers other knots, then this is conceptually, from string perspective, quite close to more general branes in toric Calabi-Yaus. And well, I would hope that there is much more general picture behind all that, and this torus knot is just the first testing ground. So I think this is, well, the time I could use. Maybe I can answer a few questions if there would be some.
Thank you, Piotr, for the very interesting talk. Any questions? The audience? Yes?
Can I say something about the proof of the case? Proof of the case. Ingredients.
Sorry, I don't ask you.
So you have this generating series for the Rak-Kyeong class, which equals to P by the P.
Yes.
And what was the ingredient?
What was the equation?
Ingredients in the proof.
Oh, ingredients.
Do you actually have a proof for it? It's a conjunction of the vector.
No, we
We don't have general proof of that. So we tested that in many non-trivial examples, but we don't have the proof that you might like.
Other questions? So these, and the tumor mutations, they are all invariant.
Well, we don't have mutations here because of the symmetric condition.
So you cannot have any case. But in general, the tumor not correspondence assumes that the NAM sum and the on-type polynomials are invariant. As you remove that condition.
Well, for this class of quivers, we cannot mutate them.
Yeah, but in general classes you can. Right?
Well, I'm not sure whether that statement that I have here with this factorization that extends to, well, you can formally factorize. You might write this generating series for any quiver which is not necessarily symmetric and factorize that. But I'm not sure if it has the same interpretation with this invariance and other.
Comment more about the brains for the root geometry. Shouldn't we take some specialized analysis of factors to get those?
Brains in, so we have one paper also with Piotr Sulkowski where we consider a kind of baby example. So let me just again say that when I say about nodes, the picture is the following. They arise because I have deformed conifold, which is like having a spring with some ray intersecting that along some nodes in which you are interested. And then I consider something which is called geometric transition and replace that by a conifold. So let me write toric diagram for a conifold, let's say in this way. And then I have some also complicated brane in that system which represents the original node. So this Lagrangian brane persists through this geometric transition and appears to like simple geometry but complicated brane. So that's the first remark. So now these branes in other geometries, as I say, we have one paper when we do something different. We consider more complicated geometries, but in fact without 4 cycles. So they arise from considering triangulation of so-called strips. So they have this type of toric diagrams. So there is I'm making a mistake. Well, this type of diagram, and then we consider Aganagich-Waffa branes. So the simplest one, but in more general geometry. And for these systems, we also find corresponding quivers in the sense that open partition functions for this brane can be written in terms of this quiver generating series for relevant quiver.
Without specializing the channel markers.
Without specialized. I mean, so again, this quiver series. Okay, so here we have some Z open partition function, which depends on modulus of the brane. Let me call this X. And then all these moduli, which I have here, Q1, Q2, and so on. So what we do is we can write this as series for some quiver, and then these parameters X1 up to Xm associated to the nodes of the quiver have to be specialized in such a way that each of them is equal to X, and then there is all those QIs in some powers. So specialization of QIs, XIs in the generating series are count information about Euler parameters.
Okay.
But that's one question. So let's see. I wonder if there is a matrix model representation of discounting. I mean, I remember we had a paper long ago about that, and then in one of the section we had a unitary matrix model for non-intersecting paths, which has a similar flavor, like going up and down.
Yeah, that's a good question. I don't know the answer, but there are of course matrix models that encode matrix models just for this geometry. So
I wonder whether you can write this path counting in the matrix model and invoke the matrix model relation to prove your statement.
Yeah, we
Just wondering,
that's a
yeah.
good. I mean, yeah, we have the representation of this thing also the matrix model.
Yes,
on one
yes.
hand. On the other hand, is this
Yes,
path.
yes.
So we can try to see whether one can be translated. Yeah.
Okay, let's wrap up today's talk. Okay, thank you, Piotr.